Hello everyone. Today we are going to explain what robot kinematic constraints are. In robot with wheels, kinematic constraints are important rules that help give the movement of each wheel, making sure the robot move in the right direction without slipping or sliding. So why are constraints important? Constraints are crucial because they allow us to control and predict the robot's motion, helping it follow a specific path and avoid unwanted movement like sliding, sideways, or spinning out of control. So these rules ensure robots operate safely and accurately in any environment, making them vital for tasks that require reliability and precise navigation. So these constraints depend on the type of wheels the robot uses. For example, fixed standard wheels can only roll forward and backward, while steerable wheels can also change its direction, and caster wheels, on the other hand, move freely and follow the robot's motion, but can ride the robot forward alone.
Okay, and in this slide we can see the started with standard well. Unlike a fixed standard well, this one can rotate around the vertical axis, giving the robot greater maneuverability. The equation shows the rolling and sliding constraint, which define how the well can move without slip. The key point is that the starting angle B is no longer fixed, but this change doesn't affect the robot's instantaneous motion constraint. And this slide shows the caster well, which is commonly found in small mobile robots. Just like the steer well, it can rotate around a vertical axis, but in this case, the axis doesn't go through the contact point with the ground. Because of that, a new parameter D is at to represent that offset distance. The rolling constraint remains the same, but the sliding constraint now includes D and the term related to the caster steering rate.
Example, the core of the solution is transforming the physical constraints of the robot, pure rolling and no slippage on the wheels, into a mathematical equation. Applying these four kinematic constraints, we construct a fundamental matrix equation that relates the robot's velocity vector to the wheel's speeds. This matrix, having 4 rows and 3 columns, is rectangular and the system is overdetermined. Please, next. To solve this overdetermined system, we cannot use a standard matrix inverse. Instead, we apply the pseudo-inverse, a method that finds the least squares solution that best fits all constraints. We substitute all the given values, R, L, the angle, and the speeds, into the pseudo-inverse formulation. The final calculation of this matrix multiplication directly yields the velocity, resulting in a linear velocity of 1.5 and an angular velocity of 2.59, thus completing the forward kinematics. Thanks.